Hello everyone, my name is Li Yi. Today, I'm going to talk about our paper, The Power of D-Holes in Matching Power Law Graphs. This is a joint work with Professor Jiaming Xu at Duke University and Professor Xiaojun Lin at Purdue University. First, let me describe what graph matching problem is. Given two edge correlated graphs, graph matching aims to find a bijective mapping between their vertex sets so that their edge sets are maximally aligned. Here is an example of two edge correlated graphs. One graph with known vertex identities, the other graph with unknown vertex identities. We aim to de-anonymize the vertex identities in the second graph by graph matching. Graph matching is a fundamental problem with numerous applications in a variety of fields, such as social network de-anonymization, computational biology, and so on. For instance, some researchers treated the content relationships graph on the Flick photo sharing service as the puppet graph, and the photo relationships graph on the Twitter microblogging service as the anonymized graph. The researchers were able to re-identify the users in Twitter by graph matching. This paper focuses on city graph matching, which is motivated by the fact that in many real applications, an initial set of seeds, in other words, correctly matched vertex pairs, is revealed as set information. Using seeds, we can measure the similarity of a vertex pair by its witnesses. For instance, here, the correctly matched vertex pair I prime is colored with green, as the unmatched vertices are colored with blue or orange. Then, the seed I prime is called a one-hop witness for the vertex pair UV because I is a one-hop neighbor of U in G1, and I prime is a one-hop neighbor of V in G2. Since G1 and G2 are graphs with correlated edges, a candidate vertex pair is expanded to have more witnesses if it's a true pair than if it's a fake pair. Thus, this seed I prime provides evidence that this vertex pair UV may be a true pair. Assuming that sufficient seeds are provided, efficient algorithms have been developed for matching ER graphs with provable performance guarantees. Although correlated ER random graph model has been widely used in the study of graph matching, ER graphs fall short of capturing many fundamental structural properties of real-world networks. Look at the cumulative distributions of degree for real-world networks shown in this figure. The x-axis is vertex degree k, and y-axis is a fraction of vertices with degree no less than k. Note that plotting the x and y-axis in the log scale, the empirical CDF closely follows a straight line, suggesting that these real-world networks have a power law degree distribution. In other words, the fraction of nodes with degree at least k decays as k to the power of 1 minus beta for some constant exponent beta larger than 0. But ER graphs do not match this property because vertex degrees in ER graphs are concentrated around the average degree. As a consequence, for power law graphs, we expanded to see very large degree fluctuations, with some nodes having very high degrees and some other sparsely connected nodes with small degrees. Intuitively, this degree fluctuation may confuse witness-based vertex matching. For example, in this figure, the true pair 1, 1 only has one witness, but the fake pair 2, 3 has 3 witnesses. This will create problems for the existing city algorithms designed for matching ER graphs. There have been several works attempting to design city graph matching algorithms to power law graphs, but often the number of seeds required is unrealistically large. More precisely, to correctly match a constant fraction of n vertices in the graphs, the user matching algorithm requires at least n over log n seeds. The DDM algorithm and y-test algorithm both require roughly square root of n seeds. In contrast, the algorithms to match correlated ER graphs only require n to the power of epsilon seeds. Our main contribution of this work is that our proposed algorithm, namely power law degree Dhop algorithm, only requires log n to the power of 4- beta seeds to match a constant fraction of vertices correctly, which achieves an exponential reduction from the previous seed size requirement. The key idea of our PLD algorithm is to use D-Hope witnesses. The reason this is important is because using one-Hope witnesses alone cannot provide enough witnesses. For example, suppose the highest degree of the graph is square root of n. In order to have at least one witness for the true pair with the highest degree, intuitively, we will need at least square root of n seeds evenly distributed in the graph. The number of D-Hope witnesses will be much larger. For example, in this figure, the true pair 1, 1 only has a single one-Hope witness, but has 4 3-Hope witnesses. However, designing an effective algorithm to use D-Hope witnesses is highly non-trivial, as we will explain next. This is going to be the outline for the rest of my talk. I will first introduce the model we use to fit different power law degree distributions of real graphs. Then I will discuss our key idea of our PLD algorithm to deal with the difficulties in matching power law graphs. I will then present the theoretical performance guarantee of our PLD algorithm and provide the numerous results that verify the effectiveness of our algorithm. In our paper, we use the triangle random graph model to generate the underlying parent graph G0 with a power law degree distribution. We start with an empty graph with n vertices. Each vertex I is associated with a positive weight Wi equal to a constant C times I over n to the power of 1 over beta minus 1. We can verify that the fraction of nodes with weight at least k decays as k to the power of 1 minus beta. Empirical studies have shown that the vertex degrees of many real-world networks indeed follow a power law distribution with exponent between 2 and 3. Then, for any pair of 2 vertices, I and j, they are connected independently with probability Pij equal to Wi times Wj over n times W bar. W bar is the average vertex weight in the graph. G1 and G2 are obtained by sampling each edge of the parent graph G0 independently with probability S. The vertices of G2 are relabeled by an unknown permutation pi. Each true pair is added into the C set with probability theta independently. Our goal is to recover the unknown permutation pi based on the observation of G1, G2, and C set. For power law graphs, the use of D-Hope witnesses is highly non-trivial because as the size of the D-Hope neighborhoods increases, fake pairs may also have many D-Hope witnesses, and thus could be confused as true pairs. For example, these are the neighborhoods of the high-weight vertex 1 in G1 and vertex 2 in G2. There is a significant overlap in their large neighborhoods, leading to too many witnesses. Therefore, a key challenge is to properly control the size of the D-Hope neighborhoods. Then, we elaborate on our 3 design choices to properly control the D-Hope neighborhood size: the weight of the candidate vertex pairs, the weight of the intermediate vertices, and the weight of the seeds. First, we need to carefully choose the candidate vertex pairs to be matched using the D-Hope witnesses. On the one hand, if the weight of the candidate vertex pairs is too small, the common D-Hope neighbors of a true pair are too small to produce enough witnesses. On the other hand, if the weight of the candidate vertex pairs is too large, the D-Hope neighbors of a fake pair would intersect a lot, leading to too many D-Hope witnesses. Thus, we choose to match vertices with weight about n to the power of gamma, where the parameter gamma will be carefully chosen later on. Second, it's important to utilize low-weight seeds while avoiding high-weight seeds. Due to power law degree distribution, when seeds are uniformly chosen, there are many more low-weight seeds than high-weight seeds. Thus, the D-Hop neighborhoods need to be large enough to reach sufficiently many low-weight seeds. Further, for a high-weight seed, it will fall into the D-Hop neighborhood of many vertices, and thus can become the witness for many fake pairs. Therefore, in order to avoid having too many witnesses for fake pairs, we only choose seeds with constant weight. Third, the high-weight vertices are not suitable to be the intermediate vertices in D-Hop neighborhoods. If we use a high-weight vertex as the intermediate nodes to reach D-Hop neighbors, the D-Hop neighborhood could again become too large so that fake pairs would have been easily confused as true pairs. When D is large, such a high-weight vertex can appear many often in a D-Hop neighborhood. Thus, it's important to avoid them. In our scheme, we use only intermediate vertices with weight no larger than n to the power of gamma. To sum up, we choose the weight of the candidate vertex pair about n to the power of gamma. The weight of the intermediate vertices no larger than n to the power of gamma. And the weight of the seed is about 1. Then the question is, what the size of the controlled D-Hop neighborhood ND is? Since ND satisfies the following recursion, ND is equal to ND minus 1 times n to the power of gamma times 3 minus beta. And N1 is equal to n to the power of gamma because the degree of the candidate vertices is n to the power of gamma. Then we can get the result. The detailed proof is shown in our paper. Then the candidate true pair have at least ND low degree D-Hop common neighbors. To guarantee the true pairs have sufficient D-Hop witnesses, we want the number of D-Hop witnesses, which is about ND times theta, to be at least log n. Thus, the fraction of seeds, theta, needs to satisfy the following condition. Note that the larger gamma is, the smaller the seed size requirement. However, gamma cannot be too large. Otherwise, fake pairs will also have many witnesses, as we discussed. Thus, we choose the parameter gamma according to this equation. And note that n over log n to the 3 minus to the power of 3 minus beta is much smaller than n. Together, the seed requirement can be dramatically reduced to log n to the power of 4 minus beta. Note that we have discussed how to match nodes with degree about n to the power of gamma. We can then sketch the whole PLD algorithm. To address the degree fluctuation in power law graphs, we first partition graphs into slices consisting of vertex pairs with similar degrees. Then we use D-Hop witnesses to match vertices in the first slice whose degrees are about n to the power of gamma. Then we can use these matched pairs as new seeds to trigger a cascading process to match the rest of the graphs slice by slice. In the end, the algorithm returns to match the 0 slice with the highest degrees. Due to sufficient new seeds, we can use only one Hop witnesses for other slices. Furthermore, there are 2 additional complications in our algorithm design. First, a true pair may have different degrees in G1 and G2. The 2 vertices of such true pair may not be assigned into the same slice. Fortunately, the degrees of the vertices corresponding to a true pair should not differ too much. Thus, we enlarge slices a little bit in our algorithm so that, with high probability, the 2 vertices corresponding to a true pair can fall into the same slice. Second, there are not enough one-hop witnesses to correctly match the slice with very low weight. Fortunately, for the fake pairs with such low weights, there are very few one-hop witnesses as well. Thus, we can treat all these low-weight vertices as a single slice and apply the PGM algorithm to match them. Then, we can describe our main result. Under the channel model with n vertices, power law exponent beta between 2 and 3, and the max degree is more than square root of n by choosing the parameter gamma according to this equation, where c is a sufficiently small constant. We show that if there are at least log n to the power of 4 minus beta initial seeds chosen independently at random, with high probability, our PLD algorithm correctly matches a constant fraction of vertex pairs without any error. The total complicated of our algorithm is n to the power of 3 minus 2 times gamma times beta minus 1. Here is the experimental results to verify our theoretical findings and the effectiveness of our PLD algorithm. First, we simulate our PLD algorithm with different gamma to investigate the impact of the parameter gamma. We generate the underlying parameter graph G0 according to the channel model with 10,000 vertices, beta equal to 2.5. Then we construct G1 and G2 by sampling each edge of G0 twice independently with probability 0.8. We use 3 Hope witnesses in our PLD algorithm. Then this figure shows the simulation result. The x-axis is the fraction of seeds theta. The y-axis is the matching accuracy. Each curve shows how the PLD algorithm performs for different choices of gamma. We can see that as theta increases, the matching accuracy of PLD algorithm improves. However, the choice of gamma by our theoretical results leads to the best performance. For our experiments on synthetic data, we still use the graphs generated according to the channel model. In this figure, the x-axis is fraction of seed theta. The y-axis is the matching accuracy. Each curve in this figure shows how the performance for different algorithms is. We can see that our PLD algorithm with optimal gamma and different d achieves similar performance, and it significantly outperforms all other algorithms. We use autonomous system dataset to further test the graph matching performance on real data. The dataset consists of an internet router network observed on 9 days between March and May in 2001. Since some vertices and edges are changed over time, these 9 graphs can be viewed as correlated versions of each other. We aim to match each graph to that on March 31st. In this figure, the x-axis is the date of networks, and the y-axis is the matching accuracy. The initial seed set is obtained by encoding each true pair independently with probability theta equal to 0.01. We can see that our PLD algorithm with optimal gamma again significantly outperforms other algorithms. Note that the accuracy rates for all algorithms decay in time because over time the graphs becomes less correlated with the initial one on March 31st. To conclude, we propose an efficient city algorithm for matching graphs with power law degree distributions. Theoretically, under the channel model, we show that with high probability, our algorithm correctly matches a constant fraction of true pairs without any error, provided with only log n to the power of 4 minus initial seeds. This result achieves an exponential reduction from the previous seed size requirement. Numerical experiments in both synthetic and real power law graphs further demonstrate that our algorithm significantly outperforms the state-of-the-art algorithm. Therefore, our results reveal the enormous power of Dhop in city graph matching on the power law graphs. So this would be the end of the talk. Thanks for your attention.